All right, solutions for quiz 3 for Math 252. In this first one, we are asked to, I guess you're not told, but you're going to end up doing partial fraction decomposition. So the way you do that is you want to rewrite 3x squared plus 7x plus 7 over x plus 2 times x squared plus 1. Sure, good enough. As something over x plus 2 plus something else over x squared plus 1. Wait, what did I do there? Why is there an a here and a bx plus c here? X squared plus 1 is irreducible. You cannot factor this into linear terms. This guy is linear, so we just need an a up top. This guy is quadratic, so we need something linear up top. We need bx plus c. So what I want to solve for is values of a, b, and c that make this equation right here true. So the way I can solve for those things is I can clear the denominator. Multiply both sides of the equation by x plus 2 times x squared plus 1. So that'll leave me with 3x squared plus 7x plus 7 equals a times x squared plus 1 plus bx plus c times x plus 2. Because if I multiply both sides by this thing, I have this x plus 2 times x squared plus 1 up top here, but the x plus 2's cancel, so just the x squared plus 1 is left behind. So I got, if I distribute here, I got ax squared plus a, and then if I FOIL here, I got bx squared plus 2bx plus cx plus 2c is equal to this thing. So what you can do is, wait a minute, I got a of these x squareds plus b of these x squareds, and that's going to be equal to 3 of these x squareds. Using the x squared terms, I know that 3 must be equal to a plus b. And similarly, using the x terms, I know that 7 must be equal, for this 7 right here, must be equal to, it looks like 2b has an x in it and c has an x in it. Something like that. And using my constant terms, I don't know if you want like a 1 out here or something, I know that 7 must be equal to, let's see, I got an a as a constant, and I got a 2c as a constant. So I get here. Now what I want to do is solve for a, b, and c. So I want to solve this system of linear equations. One way you can do it is I could take the first equation here and, I don't know, leave it as is maybe. So I get 3 equals a plus b. And then take this equation down here, but take kind of the negative of it. So I got negative 7 equals negative a minus 2c. And then if I add up these two equations, I get negative 4 equals, the a's would cancel, and I get b minus 2c. How's that help? Well, now I have this equation and this one in the middle that I haven't used yet. And they both have b's and c's in them. So I can cancel out one of those letters and solve for the other one. So let's see, I got 2b plus c here, and I got b minus 2c here. I don't know, maybe let's get rid of the b's. So let's leave this one alone. I got 7 equals 2b plus c. And then let's take this equation and multiply by negative 2. So I get 8 is equal to, if I multiply this by negative 2, I would get negative 2b. And if I multiply this by negative 2, I would get positive 4c. So that's kind of taking this equation and multiplying by negative 2. Now if I add these equations, I get 15 equals, the b's cancel, I get 5c. Well, that works out really nicely. Then c is equal to 3. And the minute that I know that c is equal to 3, I can go solving for the rest of them. If c equals 3, I got 7 equals 2b plus 3. So 4 equals 2b, so b equals 2. And if I know that b equals 2, 3 equals something plus 2, that's something, I guess it's a 1. I got a, b, and c are 1, 2, and 3 respectively. So all of this, bunch of algebra. I haven't done any calculus yet. I guess it's about time. I'm not going to try to take the integral of this thing. I'm going to take the integral of what it's equal to, this thing over here. So I'm going to evaluate the integral of, and then a, which is 1 over x plus 2, plus bx plus c, in other words, 2x plus 3, over x squared plus 1. And I'm actually going to take it a step further. I'm going to split this fraction up into two fractions. So I got the integral of 1 over x plus 2 plus 2x over the integral of, 2x over x squared plus 1 plus 3 over x squared plus 1. And so I got the integral of this sum, which is just the sum of the integrals. In other words, I can deal with each of these guys individually. This first one is pretty straightforward. I can just say it's the natural log of the absolute value of x plus 2. Note that if you took the derivative of this, you'd get 1 over x plus 2 times 1. In other words, exactly this thing right here. For this second one here, maybe this goes here. And for this one, I'm going to let u equal x squared plus 1. And then du is 2x dx. Hey, how convenient. I got a 2x right here. And if I thought about this integral, there'd be a dx here. So if I do that, I end up with just the integral of 1 over u, which is the natural log of the absolute value of u. What I'm saying is this middle term, maybe I can bring this guy down here, natural log of x plus 2, plus, from this guy, I'll get the natural log of x squared plus 1. And then for this last one here, I got 3 times, and then for this guy, I'll say either use formula, provided, this guy up here, or recognize the derivative of arctangent, derivative of arctangent of x is 1 over 1 plus x squared, which if I pull this constant 3 out in front, what I have here is exactly 1 over 1 plus x squared. So this is just 3 arctangent of x. Tack on the plus c if you think about it, and you are done with this problem. That one went there, and that one went there. All right, second problem, trig substitutions. There's a few different ways you can solve this problem. I imagine most of you will do it one way, and I'm kind of tempted to do it a different way because I worked really hard to make this problem work out really well. So let me show you a way to do it, and then I'll write up solutions doing it the other, more standard way. Option 1. What you'll see is that if you change sine squared x into 1/2 1 minus cosine 2x, then this 2 and this 1/2 cancel out. I could say that really I'm just trying to figure out the integral of 2 times 1/2, which is just 1 minus cosine 2x, plus, and then instead of cosine cubed 2x, I can write that as cosine of 2x times cosine squared of 2x. You don't need those parentheses, but it might make it easier to look at. So why did I do this? Well, on this side, I did it because anytime you have an even power, you're going to be using these. An even power is the only power in your trig sub in that term. You'll be using this double angle formula. And when you have an odd power, typically you peel off one of them and then do a u substitution. But you might recognize that, wait a minute, I got a cosine of 2x in this term and a cosine of 2x in this term. I wonder what would happen if I factored. I could make this the integral of 1 minus plus, how should I do this? Let's do it minus, how about throw my dx in there, the integral of 1 dx, or just dx, minus the integral of, and then what I would have here would be cosine of 2x, and since I factored out a minus, it would be minus cosine of 2x cosine squared 2x dx. This integral is really easy to take. This just turns into an x. But over here, I'm not going to differentiate yet. What I'm instead going to do is factor out cosine of 2x. Because if you factor out cosine of 2x, then what you would have left would be a 1 from here. And this is gone and this is gone. Cosine squared 2x here. So what, you're not impressed? All right, I'll keep going then. I still have this x just kind of hanging around. And over here, 1 minus cosine 2x, well, 1 minus cosine squared of anything is just sine squared of anything. So I got cosine of 2x times sine squared of 2x dx. So I can let u equal the sine of 2x, in which case du would equal 2 times the cosine of 2x dx. Then what I would have would be x minus the integral of, well, let's see, the cosine of 2x dx is right here. So if I put in a 1/2 out in front of this guy, I would get, let's write one more line here. If du equals this, then half of du is equal to cosine of 2x dx. So then the cosine of 2x dx changes into the 1/2 and the du that I'll write over here. And then I got sine squared dx, sorry, sine squared 2x, but u is sine squared, so I just go to u squared here. And so from here, maybe I'll hop up here, I got x minus 1/2 times, let's see, the antiderivative of u squared is 1/3 u cubed. So I got x minus 1/2 times 1/3, aka 1/6 of u cubed. And u is sine of 2x, so I got sine cubed of 2x. And if I remember to put in a plus c, more power to me, that right there would be my answer. That's one way you can do it. Let's see, this video is going to get long. I'm going to write up another way and then talk through it. Another option, which you could do, what I'm calling option 2 here, is if you didn't think to split this up into this integral of 1 and then this guy and then factor, which I don't know that a whole lot of people would, I think a more natural way to split it is to kind of split the even stuff and split the odd stuff. And so if you did it that way, you would still use your double angle formula to get here, but then you would think about this as one of the integrals. And then you would still peel off one of the cosine of 2x's and then change the cosine squared of 2x into 1 minus sine squared, but you kind of leave this all together as your other integral. And so you'd still do this u substitution, u is sine of 2x, du is 2 cosine 2x, and you'd still anti-differentiate this part. So what you now end up from this part is this guy, and doing the same u substitution you get here, and you take the antiderivatives, and what you end up with when you do all the algebra is this mess down here when you put it all back together. But what you'll see is you have a negative 1/2 sine of 2x and a positive 1/2 sine of 2x. Those guys cancel, and sure enough, we'll get the same answer that we came up with before. All right, maybe I even put a little arrow here. Good enough. Second page, now we're using the tables here. With the help of the provided tables, which, I don't know, trust me, I'll provide them. Maybe I'll write them on the board or something. Evaluate this mess right here. You're going to have 8 or so formulas to choose from. This will be the one you want, number 39 here. And the way you can convince yourself of that is you could do a u substitution. And maybe there's other ways to do it. I don't know. Might be able to use one of the other formulas. I kind of doubt it, but you never know. Let's let u equal the natural log of 2x. Well, if u is the natural log of 2x, then du is 1 over 2x times 2 dx. In other words, 1 over x dx. So if I do that u substitution, evaluate what? I guess I should put an integral in there, huh? If I do that u substitution, what I'm asked to figure out is the integral of the square root of, and then the natural log of 2x is what I'm calling u, so that thing is being squared, minus 9, and then 1 over x dx, I guess I need a dx here too, I changed it into du. And you're like, oh cool, this fits this formula really well. I can use number 39 with a equals 3 to get u over 2 times the square root of u squared minus 9 minus a squared over 2, so 9/2, natural log of u plus, and then this term again, the u squared minus 9 plus c. And then you don't want to leave u's in your answer, so you just copy that entire mess, and this is kind of tedious, but everywhere you see u, you change it to natural log of 2x. So you get natural log of 2x over 2 times the square root of, then natural log of 2x squared minus 9 minus 9/2, then natural log of 2x plus the square root of, am I going to be able to fit this in? Natural log of 2x squared minus 9 plus c. I think I copied this, and everywhere I saw u, I changed it into natural log of 2x, and that would serve as my answer for this problem. Then the last problem, number 4 here, this one's not quick if I remember right, is evaluate the convergent integral. Okay, so I'm telling you it's convergent, not divergent. That's a little hint. So you're figuring out this integral right here, and you're like, oh, there's a problem. Here's another hint. This was a hard quiz. That's why I gave you these hints. Natural log of x has a vertical asymptote at x equals 0. So I can't look at it just like this. What I have to think about is evaluating the limit as a approaches 0 from the positive side of the integral from a to 1 of x squared natural log of x. This is what I'll have to figure out here. This is what's called an improper integral. Because, well, whatever. So this is what I'm trying to figure out. How am I going to figure out this antiderivative? Maybe I do this off to the side somewhere. The antiderivative of x squared natural log of x. You might think you substitution when you see the natural log of x, but then you're like, wait a minute, that's 1 over x for du. That's not in here. Shoot. What about integration by parts? I think you can use integration by parts. Flashback. So what's going to be u and what's going to be dv? Well, whatever I choose to be dv, I have to take the antiderivative of. And the antiderivative of natural log of x is kind of a pain to do. So instead of doing it that way, why don't I let u equal the natural log of x, and then dv could be equal to x squared. And if I do that, then du is just 1 over x dx, and v would be equal to 1/3 x cubed if I take the antiderivative of this guy. So my integration by parts formula tells me that the integral of this thing is equal to u times v. In other words, let's put the 1/3 out in front. 1/3 natural log of 1/3 x cubed natural log of x. I'm going to write it like that. Minus the integral of v du. So here's the v and here's the du. If I put those guys together, I'll write it once. 1/3 x cubed times 1 over x dx. So let's see, I got the 1/3 x cubed natural log of x, but now I could factor out this 1/3 or pull that 1/3 out in front of the integral. And then all I have left in the integral is x cubed and 1 over x, which is just x squared. And that's something I'm comfortable with taking the integral of. 1/3 x cubed natural log of x minus 1/3, and the antiderivative of x squared would be 1/3 x cubed. So I'd get there. Let's see if you feel like it. Okay, so I have this antiderivative here. So that goes up here. What I'm looking to evaluate, I don't know, maybe an arrow or something, is the limit. Let me switch to blue. Maybe that'll make this look prettier. The limit as a approaches 0 from the positive side of, and then I could take this thing and evaluate it at 1 and at a and subtract those two, kind of the evaluation theorem. So first I'll plug in 1s. I have 1/3 times 1 cubed times the natural log of 1. Isn't that just 0? Yep. Minus 1/9 times 1 cubed. So this mess minus. And then I want that same thing except a's in place of the x's. So 1/3 a cubed. Natural log. My a's look a lot like 9s. Sorry. There's a 9 over here. Ugh. Okay, let's try my best to make a legible a. A. Guess that works. Cubed. Natural log of a. Sure. Minus 1/9 a cubed. So how am I going to evaluate this limit? Well, let's clean it up a little bit. I got the limit as a approaches 0 from the positive side of, let's see, okay, so this is all 0 because the natural log of 1 is 0. So this is all 0 right here. And then this is just the 1/9, so I got negative 1/9 minus 1/3 a cubed natural log of a. Sorry if those look like 9s. And then this minus and this minus makes this plus 1/9 a cubed. God, sorry, those look so much alike. I'll try harder. I don't like fractions. You might. I don't. That's not true. I really have nothing against them, but I'm going to pretend I don't. I'm going to pull a 1/9 out in front of this whole thing. Negative, positive. Let's pull a negative 1/9 out in front of this whole thing. Then I got the limit as a, which looks nothing like this 9, approaches 0 from the positive side of, see, this would be a 1 right here if I took out a negative 1/9. This would be 3, positive 3, of these a cubed natural log of a things. And then if I pulled out a negative 1/9, this would be minus a cubed. So I get here. Oh, sorry, watching a baseball game at the same time. So how do I deal with this limit here? I'm actually going to take it one step further. I'm going to say this is equal to 1/9 times the limit as a approaches 0 from the positive side of 1 is just 1, plus the limit as a approaches 0 from the positive side of the rest of this stuff. 3a cubed natural log of a. Yeah, 3a cubed natural log of a minus a cubed. And then what I'm going to do, since I'm so low on room, is I'm going to take this thing right here and deal with it somewhere else, up here maybe. So I want the limit as a approaches 0 from the positive side of 3a cubed natural log of a minus a cubed. Well, I kind of like having it times something, so I'm going to factor out an a cubed. And if I factored out an a cubed, I would get 3 natural log of a minus 1. And it turns out this is an indeterminate form. Don't believe me? Well, let me try to talk you through it. As a gets really close to 0, this is clearly 0, but as a gets close to 0, the natural log of something really close to 0 gets close to negative infinity. So I have this 0 times infinity, negative in this case, form, which is indeterminate. And if you don't believe me, you can rewrite this into a form that's conducive for L'Hopital by taking this a cubed and putting it on the bottom of the fraction. So 3 natural log of a minus 1 over a to the negative third power. And maybe now you can see that this is negative infinity and this is positive infinity, which is an indeterminate form. So I can use L'Hopital's rule to say that this is equal to the limit as a approaches 0 from the positive side of the quotient of the derivatives. So the derivative of the top here would be 3 over a. And the derivative of the bottom would be negative 3a to the negative fourth power. Check it right like this. I'm going to clean this up a little bit. You get the limit as a approaches 0 from the positive side of, kind of invert and multiply by the reciprocal of the denominator here. The 3's will cancel. You'll be negative. You'll have a to the fourth over a, which is a cubed. So you get negative a cubed. But the limit as a approaches 0 from the positive side of negative a cubed. That's just 0. All right, so this whole thing is just 0 right here. What I'm saying is I have negative 1/9 times 1 plus, and then maybe in green, so this color coordinates, 0. So my answer is just negative 1/9. I think that was a really hard problem. I'll probably end up making part of this extra credit. Maybe like, I don't know, if you can get to here, you get full credit, and if you can finish it, you get extra credit. I don't know. We'll decide. We'll see how you guys do. That ends this long quiz.